There are two types of calculation to be noted. One, to calculate energy of an electron in its level, and another one is to calculate the change in energy for the electron transition. To calculate energy of an electron in its level, we use the formula En equals to negative RH 1 over N2 squared, where En is energy at its energy level, RH is Rydberg constant, N is quantum number. To calculate the change in energy for the electron transition, we use the formula delta E equals to EF minus EI, where EI equals to negative RH 1 over Ni squared, EF equals to negative RH 1 over Nf squared. Then we substitute both equations into delta E equals to EF minus EI, and I equals to initial energy level, and NF equals to final energy level. Thus, we will get delta E equals to RH 1 over Ni squared minus 1 over Nf squared. Next, we go to example. Example 1. Calculate the energy of an electron in the energy level n equals to 6 of a hydrogen atom. So, to calculate energy of an electron at n equals to 6, we use the formula En equals to negative RH 1 over N2 squared. So, E6 equals to negative 2.18 times 10 power of minus 18 times 1 over 6 squared. Then we will get negative 6.055 times 10 power of negative 20 joule. Next example is to calculate the energy change that occurs when an electron makes a transition. The question is, calculate the energy change that occurs when an electron falls from n equals to 5 to n equals to 3. So we use the formula delta E equals to RH 1 over Ni squared minus 1 over Nf squared, where Ni equals to 5 and F equals to 3. So delta E equals to 2.18 times 10 power of negative 18 times 1 over 5 squared minus 1 over 3 squared. Then we will get negative 1.55 times 10 power of negative 19 joule. The amount of energy released by the electron in a transition is also called a photon of energy. A photon of energy is emitted in the form of radiation with appropriate frequency and wavelength. The relationship between a photon of energy and its frequency is given by equation delta E equals to h nu. H is Planck's constant with the value of 6.63 times 10 power of negative 34 joule second, and nu is frequency. A wavelength and frequency are related by the equation lambda, which is wavelength, equals to c over nu. Thus, delta E equals to hc over lambda. where c is speed of light, which has a value of 3.00 times 10 power of 8 meter per second. The wavelength corresponds to the transition of electron between two energy levels is calculated by using the Rydberg equation. 1 over lambda equals to RH 1 over n1 squared minus 1 over n2 squared, where RH equals to 1.097 times 10 power of 7 per meter. Lambda is a wavelength. Since lambda should have a positive value, thus n1 is less than n2. The ionization energy of hydrogen atom. Ionization energy is the minimum energy required to remove 1 mole of electron from 1 mole of gaseous atom or ion. It can be represented by the equation m in the form of gas. Remove 1 mole of electron will produce m plus in the form of gas 2. Delta H equals to positive value. The hydrogen atom is said to be ionized when electron is removed from its ground state, which is n equals to 1 to n equals to infinity. At n equals to infinity, the potential energy of electron is 0. Here, the nucleus attractive force has no effect on the electron. The electron is free from the nucleus force of attraction. The ionization energy of hydrogen atom can be determined in two ways. One, by the equation delta E equals to RH 1 over Ni squared minus 1 over Nf squared. In this case, electron is excited to n equals to infinity. We also can determine the ionization energy of hydrogen atom from the convergence limit. How do you calculate the ionization energy of hydrogen atom in its ground state? To calculate the energy needed by one electron, we use the formula delta E equals to RH 1 over Ni squared minus 1 over Nf squared. So we substitute Ni equals to 1 and F equals to infinity into the equation. Thus, we will get 2.18 times 10 power of negative 18 joule. This is energy needed to remove one electron from one hydrogen atom. To find the energy required to ionize 1 mole of electron, we multiply this value with Avogadro's constant. Thus, we will get the ionization energy for 1 mole of electron equals to 1312 kilojoule per mole. Another way to determine ionization energy is from the convergence limit. Convergence limit is the wavelength or frequency at which the converging spectral lines merge or converge together because the difference between energy levels become smaller and smaller.